pertaining to naming alcohols and ethers. So in this case right here, in this slide, we define alcohol. Alcohol is anything with a OH group, an OH group. This OH group also has another name called a hydroxyl group. Hydroxyl group. So oftentimes we have two names for the same thing, alcohol or a hydroxyl group. This is an example of a ethanol molecule found in drinking alcohol. Our next classification is phenols. Phenols. Phenols are basically an alcohol connected to a benzene ring. You had to memorize this one earlier, so we briefly investigate this one again in a little bit more detail, but it's an alcohol with a benzene ring, and we call this a phenol. Notice the spelling. It's Phenol. And finally, we have ethers. Unlike alcohols, where one side has a hydrogen, both sides have alkyl groups. So in this case, this picture shows an oxygen between two alkyl groups. These right here, these actually represent miscellaneous bonds. These bonds could be hydrogens, or they could be other alkyl groups, and I'll represent it as a R for alkyl groups. So this one could be an R, or this one could be a hydrogen, this one could be an R, this could be an R, and again, R is for alkyl groups, or they could be hydrogens. I'm going to go ahead and circle a nice, and highlight a nice example. In this case right here, this is called a dimethyl ether. Dimethyl ether. It's a great cleaning solvent. Its UPAC name is 1-methoxymethane. 1-methoxymethane. However, its common name is dimethyl ether. Notice it has alkyl groups on each side of the oxygen. Not always, but sometimes you'll see the two lone pairs on there. Two lone pairs. Although I don't require you put them on there, it's a good habit to have them put on there, because that way it helps you figure out what the intermolecular force is, and by extension, then the relative boiling point and solubility. Same thing with the phenols and the alcohols. In this example, I have the lone pairs. They're not required, but they do provide insight again into the intermolecular force, and by extension, the boiling point, the relative boiling point, and the solubility. Going to the next slide. Here we have methanol, an example of our alcohols, and we're going to focus on those first. Here's a chemical property of methanol. In this case, it shows the chemical property, aka chemical reaction, where if we mix two methanols and oxygen, we can go ahead and have a combustion reaction, creating carbon dioxide and water. This is a high energy combustion reaction. Hence, it's great for anything where it requires a lot of boost of energy, such as you'd find in drag racers. So a lot of them contain engines that can process methanol. Methanol is also a byproduct of distillation of ethanol, which is why distillations and distilleries of ethanol are closely watched, because if you produce this byproduct of methanol, well, best case scenario is it'll make you go blind. Worst case, you'll have a slight case of death. It's also a great cleaning solvent. Ethanol, you can go ahead and take a look at that. And then finally we have isopropyl alcohol, the common name, aka the UPAC name is 2-propanol. And then finally we have a glycerol right here. This is a very nice and relatively safe lubricant. It's also a precursor to a variety of important biomolecules, such as triglycerides. Oftentimes in the future we'll refer to primary, secondary, and tertiary carbons and primary, secondary, and tertiary alcohols. So let's go ahead and show you what those are all about. In this case right here, I'm going to go ahead and highlight with my yellow pen. This is an example of a primary alcohol. A primary alcohol. And it's a primary alcohol because it's connected to a primary carbon. Highlighting the next one over here. Here we have a carbon, and its functional group is a secondary alcohol. Secondary alcohol. Why? Because it's connected to a secondary carbon. So to figure out whether it's primary, secondary, or tertiary alcohol, we must first figure out if it's a primary, secondary, or tertiary carbon. Duh. So in this case right here, going back to our first example, we want to go ahead and look at a target carbon and figure out if it's primary, secondary, or tertiary. We count how many other carbons is it directly attached to. So in this case, it's attached to one other carbon or alkyl group, so therefore it's a primary carbon. It can often be written like this, or we can use the actual term primary, or use the actual written term primary. Let's go to the next one. In this case, we have two carbon or alkyl groups, so we call this a secondary, written as secondary. And finally, this one has three carbons or alkyl groups connected, so therefore it's tertiary. Let's see examples down here. I'm going to go ahead and highlight the carbon we're looking at. This is the carbon we're looking at because this is the one connected directly to the alcohol. How many other carbon or alkyl groups is it directly connected to? It's only connected to one other. So therefore it's a primary alcohol. Notice we're looking at carbons directly connected to it. So let me go ahead and highlight the carbon that's directly connected to it. So this carbon is the only one that's directly connected to it. So therefore it's primary carbon. We're not looking at the other one over here, only the one directly connected to it. Let's take a look at our on the next example, we're looking at our carbon directly connected to the alcohol. So this is the carbon here. How many other carbons are directly connected to it? In this case, it would be 1, 2. Let me go ahead and use my green pen on that one. So in this case, 1 carbon, 2 carbons, so therefore it's a secondary alcohol. So now you should be able to identify whether you're dealing with a primary, secondary alcohol, which is dependent on whether it's a primary, secondary, or tertiary carbon. Naming it. So here we have alcohols. There's a term called precedence. Precedence. And so let me go ahead and spell precedence. So precedence, P-R-E-C-E-D-E-N-C-E. Precedence means functional group priority. In the past, I always had you memorize the alphabet method. And that's how you figured out which one was more important than the other if there was a tie. In reality, organic chemists came together and they basically made a arbitrary list of which one was more important than the other. There's no way you could reason it out, you simply had to memorize the list. So, and these are considered formal rules, something I've tried to avoid a lot of formal rules if I could. Alcohols I cannot. So when it comes to figuring out which one is more important, number 1 on the list is going to be alcohols. So number 1 is going to be alcohols. After that, then we're going to go ahead and focus on all the other functional groups, such as the alkenes, the alkynes, and the halogens. And then, last but not least, then we'll actually focus on the alkyl groups, such as the common name alkyl groups, such as isobutyl, isopentyl. So from this point, if there's ever a tie, you're going to have to automatically assume that alcohol is most important. Here, we go ahead and we figure out what the parent is. I'll highlight the parent. We then have to figure out which carbon end is closer to the alcohol group. In this case, it goes from right to left. Carbon 1, carbon 2, carbon 3. So therefore, on carbon 3, it's going to be 3-hexanol. 3-hexanol. The other way to write it, and in many ways you can think of this as a as like an alkene or alkyne, is hex and 3-ol. Hexan 3-ol. My advice is to keep it in this format, because most likely when we start getting into more of these functional groups, and I start giving you multiple functional groups, you're going to have to keep the location number with the functional group suffix. So although the left is great if there are only alcohols, the right is going to be mandatory if there's more than one functional group present. So my advice is to go ahead and stick with this one right here. In this example right here we have 2 alkyl groups. So we're kind of from right to left. So it's going to be 2 of the same type of alkyl groups. Those will be suffixes. So 2,4-dimethyl 3-hexanol. The other way to write it is 2,4-dimethyl hexan 3-ol. So moving on, I do need to point out that there is another way of naming alcohols altogether, and this is one of my favorite ways to name it, and it makes things a lot easier just for myself. So I want to show you this method. This is also an accepted method, and if you notice over here we have again carbon 1, carbon 2, carbon 3, but rather than say 3-hexanol, we're going to go ahead and use the term 3-hydroxy. The hydroxy is going to be a prefix. So in this case, it's then going to be 3-hydroxy 2-dimethyl hexane. So I love using this hydroxy as the alcohol alternative, simply because it's easier to name things, and I don't have to worry about breaking up the suffix. As you already know, that can be really hard, especially if you're dealing with alkenes and alkynes. I accept both ways, but also keep in mind you could see it written both ways on future exams or future quizzes or so forth. In this case over here, here are examples of many alcohol compounds called polyhydroxyl compounds. So just as you had multiple alkenes, multiple alkynes, multiple halogens, you can have multiple alcohols. Using the alcohol suffix naming scheme, if there's 2 alcohols, then it's going to be a diol. If there's more than two alcohols, maybe there's three alcohols, and it could be a triol. Nature loves alcohol groups. The more alcohol groups you have on a molecule, the more soluble it is, the more possible chemical reaction sites you can have. So nature loves it. And one of the most popular alcohol embedded molecule there is are sugar molecules. So here's an example of a straight chain sugar molecule we call glucose. This is one of many different structural isomers, but as you can see, there's a whole bunch of alcohols. Nature, in its biomolecules, loves polyfunctional groups. So in this case, not only do we see multiple alcohols, we also see another type of functional group called a aldehyde. But going back to the top, make sure you know how to name multiple alcohol groups, and they could be diols. I may go up to triols. My advice, even though they have it here, is to go ahead and stick it next to the di. Stick it next to the di. Here, go ahead and stick it next to the di, so then it would be written something like this right here. So then it'd be written like this as prop and 1,2 diol. And this one up here would be written as F and 1,2 diol. I think it's important to show you the other way that I can name this. The other way I can name this is 1,2 dihydroxy ethane. This one over here could be named 1,2 dihydroxy propane. If I give you a sketch such as these ones over here and I ask you to name it, you have multiple ways of naming it. My favorite is the way you see it right here. So that way if there are any alkenes or alkynes, it makes it a lot easier on my part to change the suffix, since it always seems to be harder to change the suffix appropriately than it does for adding prefixes. Keep in mind, I could give you multiple different ways of naming these alcohols, and you could draw the sketch based on whatever naming scheme I use. So please be aware of that. So in this case, let's go ahead and go back to ISIS and try a couple examples. So in this case right here, I'm going to go ahead and add in an alcohol. If you're sketching an alcohol using ISIS, you're going to have to manually change the alkyl branch into a hydroxyl. Also keep in mind that the alcohol, and I'll highlight it in red, the alcohol hydrogen should always be shown. It's never implied, it's always shown. So if you're drawing the line angle structure, it's always going to be shown. Now you can have it as line angle, or you could have it as a condensed structure. So here's an example of a condensed structure. I do want to point out that if you decide to name it as you practice it, it always loves using alcohol in the suffix version name. More importantly, when you name this, it will convert it into a line angle, and it will get rid of that oxygen. These are glitches in the program, so you have to reattach the hydrogen. So again, it is a glitch, and you are responsible for adjusting the hydrogen so that way it reappears again. Here is the suffix name, octan 3-ol. Let me give you the alternate way of writing it, and that would be 3-hydroxy octane. So that's the that's the alternate way of naming it. If I wanted to, I could go ahead and add in a alkene. In this case right here, the brand new name then would be oct1ene3ol. Here's the priority list when it comes to suffixes. It's going to be ene first, it'll be ein second, and then it will be ol third. Ene, ein, and ol. So in this case right here, I'm going to go ahead and arbitrarily add in a carbon here. I highlight everything, and again ignore the E. So it'll be 3-methyl octa-1,4-diene. That's weird. Let me go ahead and adjust this. Alright, let's try it again. That's weird, I didn't see the oxygen. Let me rename it. Now it's going to be octa-1,4-diene-3ol. So notice the rules. First the ene, then the ein, then the ol. Let me go ahead and change this one right here to a triple bond. A triple bond. Out of habit, I'm just going to adjust it so that it's linear. Alright. And then, of course, I have to add in my hydrogen because it's a good habit to get into. Now, let's go ahead and name it. So it'll be oct-1-ene-4-ein 3-ol. Notice the alcohol suffix is always at the end. Now you can also see why I love using the hydroxy version. In my opinion, that's so much easier writing 3-hydroxy and then writing the rest. Oct-1-ene 4-ein. So here is the alternate way of naming it.